Hello, and welcome to the Trepa Technologies Security Plus course. My name is Johnny Bandon, and I will be your instructor for this video series. In this video, we'll be going over Domain 1.4 network attacks. So let's get started. The first attack we will go over is a wireless attack called Evil Twin. Wi-Fi networks use an SSID to broadcast their networks. Wireless access points will broadcast an SSID and handle all traffic for Wi-Fi enabled devices and users. So again, that access point or that WAP is going to broadcast an SSID, which is a 32 character length maximum name for your wireless network. So here we have Trepa underscore Wi-Fi. In a wireless deployment, your organization will deploy many APs to service older Wi-Fi devices. APs in an enterprise will most likely share the same SSID name. This allows your Wi-Fi enabled devices to roam throughout the network without having to re-authenticate each time a Wi-Fi enabled device moves. So if you move your laptop from your desk to the conference room, you want to make sure that you stay connected. You don't have to re-authenticate, right? So attackers can exploit this by bringing in their own AP, giving it the same SSID, and having users connect to their rogue AP instead of the legitimate AP that your enterprise deploys. And then from there, they could still send the user's traffic to the internet, right? So the user will be unsuspecting, but also steal all the data that comes across their Evil Twin AP. So you may be wondering, well, why would my Wi-Fi enabled device connect to this one, the Evil Twin, over this one? Well, computers are going to connect to the strongest signal and a known good SSID automatically, right? And of course, this depends on how you set up your systems. We're just talking very basic stuff right now. For example, in my own house, I have my home Wi-Fi and I have a 5G hotspot that I bring with me when I do in-person training. Well, if I turn that hotspot on right next to my computer, since my computer remembers both my home Wi-Fi and my hotspot, it's going to connect to that hotspot because that signal is stronger. So that threat actor can bring that Evil Twin, set it right up at its desk, if it's possible, right? And users there could potentially connect to that one because the signal's stronger. Now let's go over some Bluetooth attacks / exploits. Blue snarfing is when a threat actor gains unauthorized access to a Bluetooth device and gathers information from that device. And this could just be stealing files or just learning about the device itself to try to do some banner grabbing or learn about the OS or the system. Bluejacking is a denial of service attack on a Bluetooth enabled device. Bluejacking will just send unsolicited messages to the Bluetooth device to disrupt their connection, like a denial of service. A disassociation attack is going to send Bluetooth frames to disconnect a legitimate user from a Bluetooth connection. An attacker does this by forcing the client to re-authenticate by sending a disassociation frame. And then during that re-authentication, the attacker can then capture the Bluetooth data sent from that reconnection. Or the attacker can just keep sending those disassociation frames and do a sort of denial of service attack on that user. Now let's talk about some RF-based attacks. Any wireless enabled device that uses some sort of signal to connect to the internet or connect to a device or your enterprise is using something called RF to transmit and receive data. RF stands for radio frequency. Radio frequency. And it's going to be used for any signal. That's what RF is. It describes any sort of signal or frequency used for transmission. So Wi-Fi uses a 2.4 or 5 gigahertz signal. Bluetooth, NFC, and Zigbee all have their own RF channels and frequencies that they use. Even your key fob, which starts your car remotely, is using RF to connect to your car and start that engine. These RF signals and frequencies and channels are usually open to the general public to view. In America, the FCC may control this. With this in mind, attackers can attempt to jam these signals or degrade the performance of these signals in a denial of service attack. They can do this by sending that same signal across, right? To try to jam it up or degrade it. And we call this jamming. So jamming really just refers, it's just a general term to describe any malicious or even unintentional act that degrades an RF signal being used for the transmission and receiving of data. So now let's get into some more specifics. RFID, radio frequency ID, is used for access and authorization in badging systems. So in a badging system, you'll have proximity readers installed at doorways that are the key component to sending information and transmitting information from a badge that will allow or deny user access to a sensitive area. So what this will look like, right? We have our doorway here, and I'm not the best drawer. We have our proximity reader. Someone will come with their badge. It'll get scanned by this proximity reader, and then this will go connect to a server, and that server is going to deny or allow access to this user. And it does this by using RFID from badge or card to proximity reader. Another attack is card cloning. This is a technique to steal a person's valid RFID badge by cloning that card and its RF signature onto a fake badge. And then we have NFC, near field communication, another RF communication protocol that uses low bandwidth signals to communicate between devices. NFC is used on card readers. It's called tap technology, right? When you tap your credit card to pay for gas or pay at a cash register, you're using NFC. NFC is also on your phones when you use Apple Pay or Google Play. That tap technology is using near field communication. And now let's move on to some layer 2 attacks. Before we go over the different layer 2 attacks, we actually need to understand what layer 2 is and how it communicates on our networks. So this isn't a Network Plus or a CCNA course, so we're not going to dive too deep into network concepts, but we have something called the OSI model, right? It has 7 layers, right? The 7 layers, which describe the encapsulation and de-encapsulation of network communication. So if we start here, we got the physical, data link, network, transport layer. I'm going to stop right there because that's really all that matters when it comes to networking. But, we have our application layer here. And this is going to be all the DNS, HTTP, stuff like that. So layer 2 right here sits at the data link layer. So layer 2 is how we communicate on our networks using layer 2 addresses like MAC addresses, or sometimes referred to as physical addresses. These are going to be 12 hexadecimal digits. So it's going to be, 0 through 9, A through F, that are burned into your hardware from the manufacturer. So every NIC on your computer will have its own unique MAC address. And then switches are the network devices that will forward traffic using this MAC address, or more specifically, using the destination MAC address to forward an Ethernet frame. So when we say the word frame, we're talking layer 2. So how does layer 2 communicate? We're going to break this down real simple. How does layer 2 communicate using a switch on our networks? So let me clear up the screen here. Get ready to draw this out for you. So when two computers want to communicate on a shared data on a switch, the switch uses MAC addresses to forward traffic between computers. The switch will have something called the MAC address table. MAC address table, or CAM table, which stands for Content Addressable Messaging, which essentially think of it as a long Excel spreadsheet of where MAC addresses reside on the switch, essentially saying where computers reside on the switch. For example, if I have computer A here, and we'll just say A is its MAC address because I don't want to type out 12 digits, it's connected on port 1/1. And computer B, and again, just for the example's sake, B is its MAC address, lives on port 1/2. In the MAC address table, that's what it's going to list out, saying computer A or MAC address A is on port 1/1 and B is on port 1/2. So when these two need to communicate, computer A is going to generate a frame with the source MAC address being its own MAC address, destination MAC address being computer B. Now, again, this isn't a CCNA or Network Plus course, so I'm not going to get into how they discover and broadcast MAC addresses. Just quick down and dirty on how Layer 2 works. Computer A is going to send this frame to the switch. The switch is going to receive it. It's going to reference that MAC address table. And it's going to say, oh, hey, MAC address B lives on port 1/2. So let me send this frame out 1/2. And that is the down and dirty about how Layer 2 switching works and how a switch uses MAC addresses to forward traffic. So with that in mind, now let's go over some Layer 2 attacks. So the first we're going to go over is ARP poisoning. ARP poisoning is an attack that manipulates the ARP process, which stands for, write that out for you, Address Resolution Protocol. So ARP poisoning manipulates the ARP process on a local area network. When a computer or any device on the network needs to discover where its default gateway is to send traffic out to the internet, the first thing it's going to do is going to perform an ARP request, right? And this is when a computer initially boots up and needs to send, right? It's going to send a broadcast to the network looking for the default gateway's MAC address, because this computer should already have its IP, its subnet mask, and its default gateway here, right? The IP address. Let's just, for example, 1.1.1. But it needs to know this MAC address so it can actually send traffic to it. So it's going to do an ARP request, right? Sending that broadcast out the internet, looking for the default gateway's MAC address. It literally will say, looking for my default gateway Layer 2 address. Well, a malicious threat actor can intercept this ARP request and redirect that computer's communication to a rogue default gateway. And then that default gateway can perform packet capturing, it can steal data, and this is going to be hard for a user to detect because that rogue gateway can still route packets out to the internet. So you may not even notice. The user will be unaware that that malicious actor is stealing information that it sends, right? So that is what ARP poisoning is. And later on in the series, we'll learn ways to defend against this using dynamic ARP inspection, DHCP snooping, and technologies like that. Another Layer 2 attack is MAC flooding. A MAC flooding attack overloads the switch's processing by sending too many MAC addresses to the switch. Essentially, that computer, you install some sort of software that's just going to flood that switch with source MAC addresses. And then that switch's MAC address table will become full, and it won't accept any legitimate MAC addresses from other devices on the network. Essentially, denial of service attack at the Layer 2. And then we have MAC cloning. MAC cloning will duplicate a valid MAC address on the network for threat actors to circumvent policies like port security, or even you can do this on Wi-Fi networks, right? So you just clone a known good MAC address, you can continue to have access. And now moving on from layer 2, let's go over some DNS attacks. So DNS poisoning is an on-path attack that routes a user's DNS packets to a malicious DNS server. This malicious DNS server can then perform packet captures, monitor the user's information, and even send bad requests to fake websites. So DNS, right? That stands for domain name server or service. It's going to map host names to IP addresses because computers talk in binary, right? They don't talk like us in human language. So to a computer, google.com will be 8.8.8.8. Well, when a user needs to send a DNS request, it's going to look for a DNS server, the first one in its path, right? The first authoritative server in its path. Authoritative server is a DNS server that's able to fulfill requests. Well, what a malicious actor can do is they can intercept that DNS request and make that user's computer believe that their DNS server, this red one over here, is the first available server in its path. And then from there, once you're sending DNS requests to that rogue DNS server, we can perform packet captures and do things like I described earlier. A way to protect against this attack is by implementing something called DNSSEC, which is a security extension attached to DNS packets or protocols, which will actually have those users' computer and its DNS packets authenticate to a DNS server using PKI, or the public key infrastructure, which we'll talk about later on in the series. You're going to notice during your studies that a lot of these things interact with each other, these technologies we're going to learn in Security Plus. So we may mention stuff like DNSSEC, public key infrastructure now, but we will deep dive or go over it later on in the series as well. So if you don't know it right now, that's okay. And then we have some more DNS attacks. So on host systems, there exists a file called a host file. And on a Windows and Linux machine, this host file can do DNS lookups before DNS requests are sent. So essentially, we got this file, and I can put in this file that google.com equals this IP address, which is going to take you to a malicious website. And if that's in your host file, the computer won't even make a DNS request when you type in google.com because it thinks that it already has it in its host file. So if a user gets access to this host file, it can manipulate and redirect user traffic to malicious sites. And then we have domain reputation. This is just a tool you can use that provides you information on whether or not a domain is legitimate. So if you go to google.com right now in a new tab, type in domain reputation tool, you'll find tools where you can see known malicious domains out there in the world. We kind of talked about this in our social engineering attacks, where you can integrate a blacklist, a DNS blacklist, into like some filters and gateways on your systems. And then we have malicious code. And this will be our last topic, and it's kind of a broad one. So coding languages, they are used to create programs, websites, and applications. But they can also be used to produce malware scripts that can wreak havoc on your network. Just like when someone invented Uber, there was also someone inventing that new malware or virus to be installed out there in the world. In the Security Plus exam, we're just going to focus on a couple different scripting languages that are built into your systems that you need to know about for the test and for securing your enterprise. So PowerShell is a built-in scripting language that comes with the Windows client and server OS. PowerShell, when used with privilege escalation, can be used to automate tasks on the network or to create malicious scripts or to do data exfiltration, right? You can do a PowerShell script that starts a TCP connection to a malicious server upon boot, right? Things, just some examples of what you can do with it. A way to prevent this from being a threat vector or an application that can be exploited is you can implement some group policies on the network. Some group policies that will deactivate or even control that stops regular users from using PowerShell, disables it on their actual system. Next one we're going to talk about is a VBA, which stands for Visual Basic for Applications. This is another Microsoft product that can be used to create macros on the Microsoft Office suite of applications. And with that, we can also create macro viruses. So VBAs are something else you have to look out for that you might want to disable on the network so that regular users cannot create these macro viruses. All right, so that's going to wrap up Domain 1.4, going over network attacks. I want to thank you for viewing, and stay tuned for our next lesson, which will cover Domain 1.5, threat actors, vectors, and intelligence sources. Thank you.